talk about double bond equivalence, also called degrees of unsaturation, or DU. And this is something between an important chemistry concept and like a trick to help you do problems. But the big questions that doing this can answer is A, is this a reasonable molecular formula? So if I give you a formula, you can use this technique to figure out if the formula I'm giving you can possibly be a stable neutral molecule or not, right? So for instance, if I said CH4, is that real? You'd say, well, carbon takes 4 bonds, so sure. But if I said CH10, then you'd say, no, carbon cannot take 10 bonds. That's not how the song goes, right? So that's the kind of thinking here. This will help you do more complicated problems than CH10. So A can tell you whether a formula is reasonable or not. And then 2, it will tell you how many pi bonds and or rings, right? So if you think about it, that's how a molecule can sort of lose hydrogens, right? So if I have the maximum number of hydrogens that an alkane can have is 2 times the number of carbons plus 2, which makes sense if you think about a big long chain, right? The big long chain has 2 H's everywhere, but it's got extra H's on each end, right? So that's the plus 2, right? So if I wanted to remove hydrogens, I could put in pi bonds, or I could make this whole thing a ring like that. So the maximum number of hydrogens that I can have is 2 times the number of carbons plus 2. Okay, so this is not as complicated as I'm making it look or sound, but very briefly, this is how we do it. So first of all, we get a formula. So we'll usually be given a formula, but sometimes this will come out of us getting a number from the mass spec and saying, okay, well, it's 44. What could that possibly be, right? Or what could this number possibly be? And then just trying to come up with some guesses. Well, carbon's 12, how many 12s fit in there, etc. Second thing we're going to do is not worry about oxygens. Oxygens do not affect unsaturation at all, so just ignore them. Third thing, for every nitrogen, I'm going to take out that nitrogen and 1 hydrogen. So I'm going to take out 1 hydrogen per oct per nitrogen in my count. Okay. 4, I'm going to take all the halides that I have, fluorine, chlorine, bromine, iodine, astatine, and I'm going to turn all those halides into hydrogens in my official count. Finally, I'm going to take that count, I'm going to count them. 6, I'm going to take the maximum number of hydrogens that I get from my, again, 2n plus 2, and I'm going to subtract the number of hydrogens that I have at the end of these steps. And then I'm going to take that number, divide by 2, and that gives me my degree of unsaturation. So let's take this for a spin. So this is pyridine, C5H5N. So let's plug this equation through this and see if it tells us A, whether this can be real, or B, whether this has double bonds or a ring. So for instance, get the formula. Cool. Ignore oxygens. Done. For every H, remove an N. Okay, so I'll take away 1 of these H's, and we'll talk about C5H4. No halides. And so what is the maximum number? What's the maximum number of hydrogens for 5 carbons? Well, 5 carbons should give me 10. 2 times 5 plus 2 is 12. Right? 12 minus 4 divided by 2. So 12 minus 4 is 8. 8 divided by 2 is 4. So according to this equation, this molecular formula should give me compounds with 4 degrees of unsaturation, which are pi bonds and or rings. So if I look at pyridine, I see 3 pi bonds, I see 1 ring. So that's 4 degrees of unsaturation, and that works. Cool. How about this one, C7H13O2? So again, I'm going to ignore oxygens. They go away. I've got no nitrogens or halides, so this one might be easy. So if I look here and say, all right, my maximum number for 7 is 2 times 7 plus 2. So 2 times 7 is 14, plus 2 is 16. 16 minus 13 is 3 divided by 2. That's not an integer, right? And so that gives me the idea that this is not a good molecular formula that can give me a reasonable neutral molecule. Okay? And in general, I'm not going to see odd numbers here unless I have a nitrogen, or I guess unless I have a halide. But for the most part, nitrogens can give me an odd number of nitrogen can give me an odd number of hydrogens in a system. Okay, so let's give this a spin. So let's say that my mass spec shows me that my mass of interest is 44. So let's try to come up with some combinations of these Scrabble tiles, right? These numbers that add up to 44. So here are 4 combinations that I came up with that all add up to 44. Okay, so the first thing I can do is try to go through and see if these things make some kind of sense with my degrees of freedom, or my degree of unsaturation, du. This one, the maximum number of hydrogens for 3 carbons is 3n plus 2, or 2n plus 2. So 2 times 3 plus 2. So that is cool, right? So this is just maybe propane. No degrees of freedom. That's good. Okay. Here, the maximum number of hydrogens for 2 carbons is 6. I've got 4, so that is 1 degree of freedom. Again, or 1 degree of unsaturation, sorry. So something like that, for instance. 1, 2, 3, 4, aldehyde. Also cool. Carbon dioxide. Right, so there, if I ignore my oxygens, then I have 4 possible hydrogens, 0 actual hydrogens. 4 minus 0 divided by 2 is 2. 2 double bonds, sure. This one, though, is going to run aground because once I remember compounds with with 1 nitrogen need an odd number of hydrogens. So this is not going to give me a stable neutral compound. But let's say that I measure 44. And how can I tell the difference between these 3 things? Well, on a normal GCMS, on the one in our lab anyway, we really couldn't. We might get sort of 1 decimal place after the 44, but these are all about 44.0. So we really couldn't do much. But other mass specs are better than ours. So there is such a thing as high-resolution mass spectrometry. High-res mass spec can actually go to 4 or 5 decimal places after the mass. And so now we can tell the difference between 44.0626, 44.02, etc. When we get a high-res mass spec, it usually looks like this, where it's not smack on to 4 decimal places where we'd expect, but we can definitely make the case that this looks a lot closer to acetaldehyde, to that thing, than it does to the other 2. And these are just for small molecules. You can imagine that for larger molecules, there's way more combinations of elements that you can get, and you might not even know what atoms that are on the board that you can use. And so high-res mass spec is really, really important in nailing down precisely what molecular formula you have.